So today we're going to talk about neural networks. And it would be difficult for me to just jump right into this because this is kind of it's not necessarily a deep topic, even though we're talking about deep learning. But it is a little bit beyond just intro machine learning. So I want to start kind of at the beginning. I know not everyone here, including myself, is a machine learning expert. So before we get to neural networks, we're going to talk about just machine learning in general and kind of whittle our way to neural networks. But I will go ahead and tell you that the reason neural networks are called neural networks are because they behave much how the brain works. You have X amount of neurons. Some of these neurons take in inputs. They take that input and pass it on to other neurons to process this information, and some of those neurons give you outputs. That's just, we've got 100 billion neurons in our brain working that way. Hopefully the neural networks that we build don't also have 100 billion neurons. That would be a pain. But later on in this presentation, you're going to get to see how they actually do kind of mimic the brain. The key takeaway I want to say is that neural networks are something you've probably heard about a lot over the past couple of years ago, and not necessarily a lot, but as you hear about machine learning, I'm sure the phrase neural network comes pretty soon after that. It is not everything in machine learning. They're kind of popular right now. They're a great tool. They're a phenomenal tool, and we're going to explore them today. Like I mentioned, they're popular, but don't think that they encompass everything machine learning. In my opinion, they're slightly a buzzword right now. You don't need a neural network for everything. You don't need machine learning for everything. But they're a great tool. There's a reason they exist. They don't solve everything though. It's not a silver bullet. So that said though, let's learn about them, because again, I keep coming back to the saying they're a great tool, and they really are. So, like I said, before we can get into talking about neural networks, we have to talk about just machine learning in general. And this is going to be one of my, so the way that this t-shirt throwing is going to work, I've got 3 shirts here. I'm going to ask some questions, and if you get it right, then you get a shirt. So my first question is going to be just who can give me an introductory example of what machine learning is? Just basics. Yes. You got to get it. You got to get it kind of right, though. Yes, that's absolutely correct. And I'm going to do my best to summarize that. Here's your, so all the shirts that I'm going to throw at are larges. If that's not your size, find me afterwards. I'll get you the right size at another meetup. But you're going to get the new shirt we got. It's got the scissor tail skyline on it. So I'm terrible at throwing, by the way. Okay. So, to summarize what the gentleman said, machine learning is a set of algorithms that allow you to take a set of data, to train that data. You also mentioned supervised and unsupervised learning, which is phenomenal. We're going to get to that next. But the idea is you have this trained set of data that you can then make predictions on. You have some sort of analytical process that can run off of that, but the key thing is that you're not actually programming what the learning process is. You're coding the underlying process, but not exactly. You're not telling the computer, the machine, what to look for in categories, how to categorize this information. You're just telling it the rules of how it can learn to do that itself. So, phenomenal answer. And the next thing, okay, before we get to supervised and unsupervised learning, Corey, has anyone seen the show Silicon Valley on HBO? So I actually have not seen it, but I've heard about this meme quite a bit. There's this thing called the hot dog test, which is an app that they build on the show, and it looks like this. It basically, you take a picture of a thing, and it tells you, is it a hot dog, is it not a hot dog? This is kind of just a simple way to understand machine learning. You take a picture of something, an algorithm runs, a trained algorithm runs, and is able to kind of pick up the patterns that make, is this image a hot dog, is it not? It's a simple example for us to understand. I don't know how simple it is underneath the hood. It could be a very complex algorithm to know whether something is a hot dog or not. But this is kind of just a fun way for us to show this is just very simple way to understand kind of a machine learning example. And I'm going to refer to this a couple more times as we go. So you mentioned supervised and unsupervised learning, and I'm very happy you didn't explain the differences between those, because that's going to be question number 2. Can anyone tell me the difference between supervised and unsupervised learning? This is a tough one, I know, and it's okay if no one answers this one. We'll keep moving on, but I want to give someone a shot. Yes?
Supervised learning would be like positive reinforcement, like plus one, plus one, minus one, like we see as well. You use like developing training it to the right direction.
Then, okay, so then how does that differentiate from unsupervised learning? I'm going to try to summarize all this.
I guess unsupervised would be learning on its own.
Yes, exactly. It's on its own. That's perfect. All right, my power cord went out. Boom, shirt number 2. Okay, to summarize, supervised learning is a set of algorithms where you kind of know the categories that you're trying to test for. You're not testing for anything random or new. You're testing, is this thing, is this something else? The hot dog test is a supervised learning algorithm. You're testing for whether it is a hot dog, whether it's not. Unsupervised learning, well, we'll get to summarize kind of what you said, is you don't know the categories. It's figuring that out on its own. So we're going to get to some examples of these. Supervised learning, we kind of explained this. There's a bunch of algorithms for each of these topics. These are kind of the 2 biggest ones. You've got classification and regression. Classification is what the hot dog test is. The goal of the machine learning algorithm is to kind of figure out this line right here, such that when we provide a set of inputs, we can determine the output of, is it a hot dog, is it not a hot dog? Classification doesn't have to have just one, doesn't have to just have 2 options. It can be as many as you need it to be, but it's you're trying to discreetly figure out, is this thing? You're classifying it. Regression, on the other hand, is you might remember this from algebra back in high school. We're kind of trying to find the best fit line for a series of inputs with the goal of then using this kind of interpolated algorithm to make predictions in the future. Stock prices could be a good example of that. Behavior's been kind of this way in the past. Is it going to be that way in the future? Well, we can predict it through regression here. So this is supervised learning, and that we know what we're testing for, and we know kind of how the data is going to break down. We mentioned that classification and regression are very common. Unsupervised learning, on the other hand, we don't know what the categories are going to be, and even if we have a guess, that might not be what the end kind of categorization is. So a good example of this is right here. We've got various images of Donald Duck, Daisy Duck, Mickey Mouse, Bugs Bunny, and Daffy Duck. And we run it through some sort of unsupervised learning algorithm, and it determines on its own, hey, these 3 are ducks, we've got a mouse right here, and we've got a bunny right here. We didn't determine that. The algorithm ran through that on its own. So this is an example of unsupervised learning, and this right here is an example of what's called clustering. So this is kind of the I would say the top unsupervised learning algorithm, where we're just clustering things into different algorithms. So that's going to be the most common. The next one is dimensionality reduction, which I really don't have a ton of experience with nor know much about. But as far as what my digging told me was basically whenever we're testing for a test data set, there are certain fields that are more valuable than other fields. There's a whole segment of machine learning called principal component analysis. I think that's what it is, PCA, which determines what are the most important fields you should be testing on. Dimensionality reduction is the opposite. We want to reduce the things that we don't care about. And for all my data scientists out there, feel free to just hammer me if I'm messing any of this up. I can take the heat. So to kind of summarize just a little graph here of supervised and unsupervised learning, we've got classification and regression here on the unsupervised side, clustering and dimensionality reduction. And I've got these comments over here for whether it's discrete or continuous. If you've taken statistics in the past, these phrases might ring a bell. Discrete is where you have just a whole number, 1, 2, 3, etc. You have specific points of data that can be there. Continuous is, just think of a line. It's continuing on and on. It can be, if you choose a point on a line, it can be any point. There's a continuous data flow. So classification is discrete because it's either one thing or the other, etc. Clustering is the same way. It's either one thing or the other. Regression is continuous because at any point in time, the data could change along this kind of regression line that we've drawn. And I'm not really going to address dimensionality reduction. I'm okay saying I don't know about things too. Okay, kind of another fundamental concept of machine learning is the idea of a cost function. And we use the cost function, it looks kind of like this. We use the cost function to kind of test how well we've mapped our data. So we're going to learn about this when we get to neural networks, but what we do with our set of inputs that we get from our training data, we apply weights to it, and with that we can draw the cost function. And the idea with the cost function is we're trying to minimize the cost function. So what do we do usually? We usually start off with just a random set of weights before the data set has been trained, and here's our starting point, for example. And I know this is a little bit blurry, but the idea is we can see our amount of error is the y-axis here. So we've got our starting point here, and we can see we've got a fair amount of error. But when the algorithm is running, we don't actually know this cost function. We don't know which way to go. This gets built as we train the data set. So we see we've got some error here. Once we train the data set, once we run through the data set one time, we can retrain it over and over again. That's called backpropagation or gradient descent, which we're going to get into. But the idea is we're constantly training our data set with new weights to see how do the weights fare. Are we improving? Are we not improving? So we have a various set of weights here that we're going to apply to our inputs. If we try to go this way with it, because again, we don't know this line graph when we're training our data. If we go this way, we'll see, okay, we have more error. Let's not go this way. Let's jump down here. Okay, we've got less error. Let's keep going this way. Let's update the weights in this way. We've got less error again. And we keep going, and this is how our data set gets trained. We use the same data set multiple times, and I'm talking thousands and thousands of times to minimize the cost function. And at some point, we do get to a minimum, and that's kind of our spot right here. This is where we know that we've got the right answer, at least as good of an answer as we're going to get. There's the whole idea of maybe this line goes even further over here and we can get even lower, and that's a whole set of algorithms or ideas that I'm not going to touch into today, but the main idea behind a cost function is we want to minimize the cost function to reduce our error. And this whole idea of going down is called gradient descent or backpropagation. I'm going to try to use backpropagation throughout the rest of this. Okay, so let's get into how neural networks actually work. We're kind of at this point. So this is a very simple, just core neural network, and we have 3 inputs here, and we get a single output. The way this would work is our input could be whatever we wanted it to be. Let's just say that our input 1 is A, this is B, and this is C. And let's say our output is B. Let's just say the output is B. What we would do in order to arrive at that output is we would apply some sort of a weight to this input to see how important it is. And then usually there's a layer between here, which we're going to get into. This is just a very, very simple example. There's a layer in here that would process that. But we would apply weights to each of these inputs to then determine the output. So if we have A, B, and C would be the inputs here, but the output is just B, then our weights could be, for example, 0 for input 1. That means we don't care about it. It could be 1 for 2, because that would just be, we're going to multiply them together, so 1 times B would be B. And then 3 could also be 0. So that's just saying that input 2 is the only weight we care about, the only input we care about. Let's put all the weight on that, and that's then our output. That's a very, very rudimentary example of just how a neural network works. Now, you won't ever see one this simple usually, because there's always going to be a layer in between there, it's called the hidden layer, and that's what this looks like. Ignore the B for now, that's a little bit confusing, but we are going to address that. But if you see a diagram of a neural network, it's usually always going to be like this, kind of horizontal. So you've got your input layer, and this is what you give it, and you have your output layer, which is what the answer is going to be. You usually, when you're training your data set, you always know the input layer and the output layer. The goal of training your data set is to figure out the weights that link up all these nodes together, all these neurons. So these are called nodes or neurons. And this is kind of the idea behind a neural network. You have neurons that are just being mapped together. Every neuron will be mapped to every single other neuron that progresses in the layers. So all of our input layers will be mapped to whatever hidden layer nodes. And each of these hidden layer nodes, they're called hidden because they're just not the input or the output. They're the processing pieces in the middle. They can test for various things, and then that will then progress to the output layer. You can have multiple hidden layers. You can have as many hidden layers as you need to. Again, I'm not a data scientist, but from my research, it kind of seemed that 1 or 2 is probably best. you really don't need to go more than that, but again, I'm not speaking from fact. That's just some research. Input layers, though, you can have as many you have one input layer, but you can have as many inputs as you need and as many outputs as you need. In fact, having 3 inputs is probably not very common at all. We're talking, you can have hundreds, thousands of inputs. So I mentioned we were going to touch back on the B. So the way that the hidden layer works is we've got various values on these inputs, and we apply weights to them, and we just multiply those together to see how important this input is. Well, let's say that we wanted to have just kind of a starting value. That's called a bias. Every hidden layer, every node that makes a connection here can have a bias associated with it, and that's just if we wanted to have kind of a starting value. Let's say, for example, you didn't want a hidden layer or an output layer to ever be 0. You always wanted a minimum of 1. You could put a bias of 1 just to make sure that you always have some initial value. So here's kind of the training loop, and I'm going to refer to this a couple times, and we start at the top here. We predict the output for a training set example. That means we run through the training algorithm, the whole training set once with our randomized weights. We calculate the error between the actual answers, which we have in the training data, versus what was predicted based on our weights, and then we adjust the weights to try to reduce the error. This all goes back to that cost function, and then we can adjust the weights. Yes, question? So the question was, are we using a cross-validation? Can you repeat the important parts of that? Sorry, my head got lost there.
So sometimes in machine learning,
Mm-hmm.
when you're tuning it, you're using cross validation, maybe like a five-fold cross validation.
Mm-hmm.
You take 4 bits of the data, you train it, and on the last 1/5, you then compare that model to that 1/5 to assess the performance. And in this repeated process, which then you calculate an error. You calculate the error of the entire training set that it was originally trained on, or you calculate the error on a portion of the training set, whereas the large portion of the training set you actually try to train the weights for. Does that make sense?
Yeah. So are we using cross-validation to kind of test for the error on the whole training set versus just a portion of the training set, right? So I'm going to say just the core answer is probably going to be I don't know. We're going to get to the demo, and I'd love for you to tell me kind of what's as far as I know, I think the answer is going to be no during the demo. I think we are doing it on the whole training set, just a flat out I don't know. Very good question. Okay. So this is our back propagation algorithm. It's just very simple. Run through the training set, figure out where we messed up, and adjust accordingly. So here's kind of an example of a more complicated neural network. Again, I mentioned that we've got 5 hidden layers here. I just mentioned that might not be the best, but this is, if you look up diagrams, this is what you'll see. This is kind of an idea of how it works, and every neuron here you can see is going to be attached to every other neuron. And if you don't care about how one neuron relates to another neuron, then you can just set the weight to 0 and you ignore it. You're going to have a set of weights for every single connection. Every single line here will have a weight associated with it. So an example here could be, let's say we wanted to figure out, if you write down the number 3, how do we know that's a number 3? How do we actually process that? So what we can do for starters is we can kind of divvy up the grid into, or the picture into a grid of sorts, and kind of figure out, was 10% of this block black versus white? If it is, then we just color the whole thing, and that kind of gets us this little image right here. This is not machine learning. This is just processing an image right here. We're just kind of figuring out. We run it through some algorithm, but it's not machine learning. We somehow get this, which is just a collection of a 6x8 grid of black and white squares. So here is where we can actually use a neural network if we want to, because what we have here is we have a set of 48 inputs that are either 0 or 1, if you will, black or white. And then we can process that and run it through. We'll run it through our own algorithm. So here's kind of an example of that, and this is not an algorithm that I ran through, so don't worry about the numbers or anything. I just wanted to kind of go through the flow. we've got various, various inputs here. These would be all 48 of them. They iterate through, they connect to each node in a hidden network here, in a hidden layer, which we probably don't need this many nodes in a hidden layer, but again, as the developer, you can decide how many you want. And then those all get sent to the output layer, which we've got 10 here. The output layer here could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it could be an array of 10 numbers, and they could all be 0, except the 1 would be whatever index the value comes up with. So 3, for example. So we've got that's just one idea of how you could go about this. Again, you could write this algorithm however you want to, but that's an idea of how we can actually build our neural network. And then what do we do after that? Well, we want to train it. So we would pass in various other images of how 3s look. We would have in the training set that these are 3s, so we would factually know that's the case, that's the output. And then this is how we train our data. So we want to provide a large training set so we can actually get accurate weights, we can get accurate input, and then we just want to run through that process over and over again so we can programmatically adjust our weights as needed, or the neural network can, I should say. So this is one example of real life how you could use a neural network to just process an image. Again, kind of going back to that, is it a hot dog, is it not a hot dog test? So let's actually get into a demo here. So what we are going to do is we've got a very, very small training set, very small. And here is our various inputs, and here is our various outputs, and we're going to write a neural network for a supervised learning classification example. Being that, again, we've got our inputs here, these are the outputs, which more or less you can think of as the answers for the input set. And then we're going to just ask a question to our neural network. What would this give us? 1, 0, 0. Does that give us a 0 or a 1? And this is going to be my next question. And I'm going to give you all about 30 seconds or so to look at this and see if you can figure out what the answer would be. You obviously know it's a 0 or a 1, so I'm not going to give you the shirt just based on that. But if you can tell me why the answer is whatever you think it is, and you're right, then you get a brand spanking new shirt. Okay, so feel free to raise your hand if you've got an idea. I'll wait about 30 seconds, and then we'll move on. Yes, Ryan. It is a 1. Why is it a 1? It is. That's exactly correct. And it can be as simple as that. We're just grabbing the first number. Do you already have that shirt, by the way? I do. Okay, we're good. Good to go. If I've given you a shirt that you already have, give it back to me. We'll make it right. So that's what we're going to test for here. That output should be a 1 because all we care about is this value right here, this column. So that shouldn't go to that one yet. We're going to actually get into some code here. So I've got a little demo about building a neural network in Python. We're not going to be live coding, it's already built, but we are going to kind of run through and test this. So, and it's a 74-line file. It's not very big. We're not using any libraries aside from NumPy, which does a lot of things, but we're only using it for these 4 tools. EXP is the natural exponent, so e to the whatever is how that would be used. Array converts an array to a matrix. I know it's incredibly clear that that's what it does. Random generates random numbers as well as a random matrix. And dot is just how we easily can do matrix multiplication. So we're just using some simple math helpers, not a neural network library or anything like that. And we have done it all in 74 lines, with most of it being comments. So we've got a class at the beginning. I'm just going to hop towards the bottom. We're going to address what all of these libraries are doing, or what all these methods are doing. We're just going to hop to this bottom section. So when we run our script, let me just show you what our script actually does. So our script is going to run that training set that we just had. I'm going to bounce back there. It's going to take these inputs with these outputs, and it's going to train our data. It's an incredibly terrible training set. We've only got 4 rows here. We're not going to get a very intelligently trained system, but it will be trained nonetheless. The way that this works is we're going to start off with just some random values. This neural network is going to have 3 inputs. It's going to be each of these columns here. It's going to just have one neuron in the middle, which that's going to be the hidden layer. It's just a single node, a single neuron, and then the output's just going to be a single node as well, which is going to be the number here. So just to summarize, an input layer with 3 nodes, just a single node in the middle that does the processing, that's the hidden layer, and then one output node. So what these 3 weights represent are the 3 weights that get applied to the input layers, which then get sent to that hidden layer node. So we just randomize them at first, and then through training this training set, we're going to run through it 10,000 times, which means we're going to run through back propagation 10,000 times as well, and we're going to wind up with these nodes, these values right here. Honestly, these could just be 1, 0, 0. That would have worked completely fine, but our neural network found something different, and that's okay. So, and we're just going to test for that value that we tested right here, 1, 0, 0. And you can see we're testing that situation here, and it's coming back with 0.99937. This kind of leads me to the next idea that neural networks are very difficult to be discrete. It's very difficult to get just a core, rock-solid, single-digit value or a non-continuous value, simply because we're using math and we're using weights of various decimals. You can see these are not clean numbers, and that's completely okay. They hardly ever will be. This is more or less telling us the neural network is telling us we're really, 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 really sure that this thing is like a 1. That's telling us that's the value, which is obviously closer to 1 than it is a 0. So that's what our script does. Let's actually run through how it does that. So we've got our neural network class above this. We'll dig into that right about now. We're going to initialize the neural network, and this is using Python 2. I found some examples online. I am not a Python developer at heart, though I do use it quite often these days. But again, this is Python 2, so you can save all your groans if you're a Python 3 fan, which I think everyone should be using if you can. So we're going to instantiate a new neural network object from the neural network class. So let's jump back up to the top and see what that does. So we're going to tell our random number generator that we want to just seed it at 1. That just means that every time we run the script, we'll start off with the same values. It just makes it easier for me to kind of test it and show that this is how it's working. And then we're going to define an instance variable called synaptic weights, which is going to be a 3x1 vector or matrix, which just represents the weights for each of the input values right there. And that right there, self.synaptic weights, I'm going to hop back to the bottom here. That's what's getting printed out at the very beginning whenever we run our scripts. We're saying these are our random starting weights. They are always going to be between 0 and 1. I'm sorry, between -1 and 1. So you can see the random values were just chosen. If we were to seed the random number generator with something else, we'd get different values, but we would arrive at more or less the same solution, which I'll do a demo of that at the end. We're going to define our training set inputs and our training set outputs. We're going to be using a lot of matrix math here, a lot of matrix multiplication. So what we're doing here is we've got an array of 4, we've got a list of 4 lists here pretty much, which represent our input data. So 0, 0, 1, 1, 1, 1, that matches up identically with this, 0, 0, 1, 1, 1, 1, etc. It's just a matrix of our input values, a 4x3 matrix, except it's not a matrix yet, it's just a list of lists. But array is a NumPy function that will convert this into a matrix, which just more or less means it's a list that allows us to do some more matrixy things, which you're about to see here. So we've got our input data. We've got our output data here, which converts this list of lists into a matrix as well. And then we're transposing this matrix, which if you've taken linear algebra in the past or just like this stuff, then you'll know that means taking it from a 4x1 matrix, 1x4 matrix to a 4x1 matrix. So that looks like this now. So we've got our input values here and our transposed output values, which is this. Now, so we've got some data. And now what we want to do is we want to train our neural network. So what that means is that once our neural network is trained, we're then going to ideally have accurate synaptic weights. And what we're doing, we're going to pass in our inputs, we're going to pass in our outputs, and we're going to run it through the training set 10,000 times. Each one of those times, we're going to adjust the weight slightly, and that's how backpropagation works. That's how that gradient descent down that cost function works. So let's actually see what train does here. And again, you'll notice everything is mostly comments. So we are training our information. We're just iterating through it 10,000 times, which is this parameter that got passed in. And then our actual process for running the neural network is this think process, because that's what your brain does. It thinks. And it's just a single line right here, and it does a lot. So we're going to take this one slow. So we've got our input matrix here, And we've got our synaptic weights there, and we're just going to do matrix multiplication because that's how the neural networks work. We take our input values, we multiply them by some weight, and then we just we add them all together in that node. That's matrix multiplication right there. How do we do the matrix multiplication? Well, that's just the dot function in NumPy. It's very, very easy. If we didn't have that, we would be doing some funky list multiplication stuff. So we just are multiplying two matrices there. And then we run them through the sigmoid function. I don't have any more shirts, but does anyone want to take a guess as to what the sigmoid function is? Or what we're using it for? Yes, Roger. So the answer was, does it have to do with the direction of the line so we can determine which way we go up and down the cost function? In this case, it does not. We are going to use the sigmoid function for that later, specifically the derivative of the sigmoid function. But that was a phenomenal guess. The sigmoid function is, well, I meant to show this is how we calculate this is what our matrix multiplication is going to end up with, just a series of weights and inputs added together. This is the sigmoid function, which is what it is. It's a line that will always be between 0 and 1, no matter what the x value is. And it does always have a positive slope, which is beneficial for us as well. But we use this, and as far as I know, in data science, this is not a preferred thing, but it's a very great example. The purpose of the sigmoid function and other functions like it are that if we have data that's way out there, let's say like 1 million to 2 million, we may not care about that for our data set. If we're testing values between -5 and 5, we probably don't care about those differences. So more or less, those values are going to be the same. We don't need to know that they're 1 million apart. We just need to know that they're both very much on this end. So if we were to take this line out here and go all the way to the end, there is a hypotenuse there at 1, so it'll never hit 1. But if we test for what the values of 1 million and 2 million will be, they're going to be very close. 2 million will still be bigger than whatever 1 million is, but we're talking, 0.000005 difference. It's just kind of a way for us to limit our responses. We can apply any number into here, and we'll always get a value between 0 and 1, with the important differences being on a very small scale. So we're running it through the sigmoid function, which it forces our answer to be between 0 and 1. So if our weights do get above that, which they will, then, and our input is a 1, for example, it's going to be above 0, 1. We're using the sigmoid function to just bring it back down to a value that we actually care about. So that's the think process, and that whole thing was running our neural network through one time. But we haven't adjusted our weights. We just got some random value. So what we need to do now is we need to figure out how far off were we from what our actual answers are, which is that's right here, 0, 1, 1, 0. How far were we off from that from what we actually got? And so error here is going to take two vectors. It's going to take the actual values that we want versus the actual values that we got from the training data set. And we're going to figure out the error. Now, what do we do with that error? And this is kind of getting into, I think, what you were talking about with the sigmoid function. We're actually going to use the slope of the sigmoid function to figure out how much we need to adjust the weights. The idea being that if our weights are very far out, either in a negative or a positive direction, they always start off small. We're starting between -1 and 1. If they're larger, then that usually signifies that we're more confident about these weights. As they get bigger in absolute value, then that signifies that we're more confident that these weights are actually stable. So we don't want to move the function as much because we're getting closer and closer to convergence on that cost function. But if our values are not as confident, if they're kind of the beginning values, between 0 and 1, for example, we want to adjust pretty heavily so we can see, are we going in the right direction? This is not a required way to do this. We're kind of getting into how do you want to handle adjustments for your weights. That's a complete aspect of data science in its own, of neural networks on its own. This is just one way to do it. So what we're doing, I'm going to hop over the inputs here. We're taking the error and multiplying it by the derivative of the sigmoid function, which the derivative of a function at any point will be its slope. So derivative right here would be about 1. It'd be approaching 0 as we get out here. It'd be approaching 0 as we get out here. So we're going to take the derivative of the sigmoid function, which is just a little function we have up here. I forgot to show the sigmoid function. It is sigmoid function is 1 over 1 plus e to the negative x. It's crazy intuitive, I know. The derivative, though, of whatever value we pass in, if we pass in, for the function x, the derivative of x is just going to be x to the 1 minus x. So that's our derivative function here. So we're going to calculate our error there, and then we're going to multiply our input weights by that, and that's going to be, again, using matrix multiplication, and that's going to be how much we actually want to adjust our weights. So again, the less confident we are with our weights, the more in this area they'll be. We'll want to change it more rapidly. As we get more confident, then we'll change it less rapidly. So we've got our adjustments here, and this is the back propagation process. And then all we do is we're just going to add on to the synaptic weights by whatever the adjustment was. Adjustments can be positive or negative. So that's one loop through of the process. We've trained our data once, or run through the training set once, I should say. We found out where we messed up, and now we're going to make the adjustments, and then we're going to do it again, and we're going to do it 10,000 times. So after we've done this loop, which runs very fast, as you saw, we're going to print out, and that's all happens right here. We're going to print out the new synaptic weights, and then, at that point, after we've trained our data set here, everything's trained. Again, a very, very poor training set. We've only got 4 inputs, 4 input rows, but again, it is trained nonetheless. We've got our, we're going to print out our new weights here, which you can see here. So before we just randomly started with these weights. After we trained our data, we got these weights. Again, coming from the intuition that we know how to solve that problem. These aren't the weights we would choose, but these are the weights that the neural network came up with. And then we process this, which the think function always runs through the sigmoid function. So this is more or less the sigmoid representation of this value right here. But that's what we're doing. We're just testing for that situation. We can test for other situations here. In this, I think if I change this to 0, you're going to see pretty clearly that while the training data worked really well for that situation, we were able to tell that the 1, 0, 0 was going to end in a 1. It's not so sure about 0, 0, 0. It's kind of right in the middle. We're literally at a 0.5 there. This is not a programming error. This is a training set error. We really need to have more training data. So when you get into full-blown neural networks, you're talking millions and millions of rows, if not more, of data can be applied. And a lot of the time, they're just constantly churning away, improving the weights. Let's see. The only other thing I wanted to showcase, really, with this is if we do change this seed, so let's just make it 100, our starting weights are going to be different, but the ending synaptic weights should be relatively the same. They'll probably be a little bit off, but very close. So yeah, you can see they were slightly different towards the end, comparing old way of doing it, or old seeds and new seeds, but they arrived at the same place, similar places no matter what, and we got to a similar answer there, where it's pretty certain that it's a 1 there. So this was just a very simple neural network that we built, just for this little training set right here. Obviously, you can go much more difficult than this. We only had 1 node in our hidden layer here, but we did it. We did it nonetheless in 74 lines, most of which were comments. So where should you learn more? Where I really got a footing in machine learning was on Coursera. Coursera is a website where you can watch a lot of free courses. They're called MOOCs, which are massively online open courses, massively open online courses, one or the other. Coursera is free, though you can certainly purchase a certificate if you want. But there's a machine learning course by an instructor named Andrew Ng. He works at Stanford. I think he's kind of the go-to course on the Coursera for machine learning, and it's just phenomenal. And again, it's free. The sessions do go at certain times, but as far as I know, you can view the content and the videos at any point in time. Don't quote me on that, but free is the big thing. And then I forgot to mention this, but there was a machine learning, or I forgot to write this in the slide, but there was a Medium article about working with Python and neural networks that I read through, and that really helped me to kind of build this. Like I mentioned, I'm not a Python guru at heart. I use it quite often now, but but I don't know the NumPy library very well, so I probably would not have known to use those tools. But if you Google Python and neural networks on Medium, you're bound to find that. It was a great reference. Thanks. So this is kind of a tandem talk. I kind of laid the grounds intro for this data learning, and machine learning and neural networks. And again, I know enough to talk about this and enough to even use it a little bit, but I'm not a data scientist. My coworker Dustin here is much better at this than me. He's going to give a talk about, I believe, transfer learning next time. So if you have any questions about what he's talking about, feel free to ask him afterwards. But so that's the next meetup, also at the Python user group. So a month from now, he'll be there. If you want to know more about the company that I work for, Clevyr and Clevyr Labs, you can just go to the websites or ask me afterwards, clevyr.com, clevyrlabs.com. That's my information again. I'm Aaron Krauss. I'm the code boss. That's my personal website, thesociety.org. There's a blog. I used to blog pretty heavily. And there's a blog post about why it is named that way. So if you are curious, I would direct you there. Otherwise, let's see if there's any more questions that I don't know the answers to. Yes?
I'm just curious on what made you want to learn machine learning, or kind of what piqued your interest. Is it the future? If you're looking like, oh, okay, this is the future.
Yes. The question was, what made me interested in learning machine learning? It certainly is the future, and it's been part of the past for a good chunk now. Machine learning's been going on for, I'd say, a minimum of a few decades at this point. With whatever algorithms were being used then. But the core piece of machine learning it's math, it's statistics, it's calculus, it's linear algebra, it's a bunch of stuff that's not programming. So. Honestly, the reason I wanted to learn it is that it's something that I didn't know very well. Certainly still not an expert by any means, but I think both as programmers and just as individuals as a whole, we like to learn things. And this does fit into my field for sure, because it's kind of, machine learning is kind of the forebear of AI, of artificial intelligence. And we talk about those types of things at work quite a bit. My boss, the CEO of the company, loves talking about AI. So we are definitely going to be using this at some point, and I'm sure to some degree we are using these for a few things right now, some of these algorithms. But it's something that I know that we're going to use, and it's something that I'm not an expert in, which makes me want to get better and better at it. But I've certainly realized that it is its own field on its own. Like data science and computer science are, they work together absolutely, but there's a whole lot of math that I need to learn to really get good at this. So, very good question that I could answer. All right, well, if anyone has any questions for me personally, or again for Clevyr, or Techlahoma, whatever, find me. I'll be here for a bit afterwards, and otherwise, that's it. Thanks a bunch.